Hello students. In this video, I'd like to discuss the factors that determine how tightly electrons are held close to the nucleus. And this directly describes the size of an atom and the size of an ion. So just so that we understand what's happening here, if I have an atom and I have the nucleus down in the center, and then I have a cloud of electrons around it, then the size of this atom is dictated primarily by the size of the electron cloud around it. So anything that causes the electrons to be held tighter to the nucleus will make the atom smaller, and anything that makes the electrons be held weaker toward the nucleus will expand these orbitals and make the atoms larger. So just to clarify, it is not the size of the nucleus that dictates the size of the atom. It's the size of the electron cloud around it that is the larger contributor to an atom's size or an ion's size. So a couple of quick notes here. We often refer to the radius which is the distance between the nucleus and the edge of the outermost valence level orbitals of electrons. And in referring to the radius of an atom or ion, we are referring to its size. The larger the size, the larger its radius. So there are three factors that are going to determine how tightly these electrons are held to that nucleus, and therefore how small or how large this atom or ion is going to be generally. The first factor is the most important factor. So the first factor is the valence level. So the valence level. And you know that that is the outermost, highest energy level of electrons. And so the higher the N value of the valence level, then what's going to happen is we have larger and larger and larger shells of electrons. So if the valence level is large, like a 5 or a 6, that means that the atom is going to be larger than if it had an N value of its valence level as a smaller number. So there's a direct relationship. The higher the N value of the valence level of electrons, the larger the size of the atom or ion. The second factor that affects the size of an atom or ion is the number of protons in the nucleus. So this is our second factor. Factor number one always wins. If we have a higher N value for the valence level of electrons, and we have electrons in that valence level, then its size is going to be larger. If the N value of the valence level is tied between two atoms, then we go to this second factor, and we look at the number of protons in the nucleus. And the more the protons, as you increase the P+, the protons in the nucleus, what happens is you have a more positive charge down here in the nucleus, and since electrons are negatively charged, they are attracted more to that nucleus. The more positives you have in here, the more protons you have in here in the nucleus, the smaller the atom is going to be because the electrons are going to be drawn in tighter. So there's an inverse relationship. So as you increase the number of protons, you decrease the size. Okay? And those two factors are generally able to determine which species is larger. Factor number one always wins. If there's a tie in factor one, we go to factor two. On occasion, however, you have a tie in factor 1 and factor 2, and we go on to factor 3. And factor 3 represents several issues that may be going on, but they are all occurring in the valence level of electrons, and specifically the configuration of the electrons in the valence level. And I'll share more about that in a moment. So again, the valence level, the higher the n value of the valence level that has electrons in it, the larger the size of the atom or ion. And that rule always wins, that factor always wins. If they're tied, then we go on to factor 2. And the one with more protons in the nucleus is smaller, because more protons in the nucleus means it's attracting its electrons tighter, and so they are drawn in closer to the nucleus. And if factors 1 and 2 are tied, we go on and talk about the electron configuration in the valence level. Okay? So those are the three key factors that are going to determine how tightly the electrons are held near the nucleus, and therefore the size of an atom or ion. Moving on. Atomic radius, just to fill in some gaps, atomic radius is the distance between the nucleus of an atom and its outer or valence level of electrons. Valence level of electrons, right? And it is the size of an atom. And it's related to how closely its electrons are drawn toward the nucleus. And there are these three key factors. So we have a question here. How is the atomic radius, the size of an atom, generally affected? What is the trend as you move down a group, and why? So let's take a look at the periodic table. As we move down a group, we're going to assume that these are neutral atoms, not ions, they're neutral atoms. And let's just look at what happens when we move down this group. The valence level for hydrogen is the n equals 1 level. So it has an electron in that n equals 1 shell. When we go to lithium, we have added another shell around the n equals 1, and it is the n equals 2 shell. So it's become larger because the n value of its valence level is larger. We have added a larger shell around it. As we go on down the group, we get to n equals 3 for its valence level. And as you can see, the trend is going to be larger and larger and larger as we go down a group. So the group, as we go down a group, the atomic radius is generally affected as the atomic radius, which we know is the size, increases as we go down a group. Why? Because we are adding another shell. We are adding larger and larger and larger shells of electrons. So again, as we go down this group, the valence level here is n equals 1. The valence level here is n equals 2. So the outermost shell of electrons here is n equals 2, and it's a larger shell than for n equals 1. So as the n value of the valence level increases, we get larger and larger and larger atoms. Moving on. Question B, how is the atomic radius generally affected? What is the general trend as you move right across a row or period, and why? Well, let's take a look. Let's compare carbon, nitrogen, oxygen, and fluorine. If we looked at the first key factor, which is the N value of their valence level, remember the first key factor that always determines, that always wins, is whatever their valence level is. The higher the N value of their valence levels, the larger the size. So if we take a look at that for carbon, nitrogen, oxygen, and fluorine, we notice that their valence level is all N equals 2. So valence level N equals 2, valence level N equals 2, and so forth. So our first rule does not help us determine which of these is larger. They are all tied with the same N value for their valence level of N equals 2. And so we have to go on to factor 2. Factor 2 says, look at the number of protons in the nucleus. And the more protons you have in the nucleus, the tighter those electrons are going to be pulled in toward the nucleus, and therefore the smaller the size. So more protons means smaller size. It's an inverse relationship. So if we look at carbon, nitrogen, oxygen, and fluorine, now we're looking at the number of protons. This has 6, 7, 8, and 9. So you can see that we are increasing protons as we go to the right across a row. If you're increasing the protons, then you are increasing the number of positive charges in the nucleus. You're going to increase the amount of attraction to the electrons, and therefore as you go right, you're going to pull the electrons tighter and tighter and tighter inward. And so that means that as you go right across a row, the atoms are going to get smaller and smaller and smaller. So the general trend as you go right across a period or a row is that as you go right across a period, size generally decreases. Why? Because the number of protons increases. An increasing number of protons attracts electrons tighter and tighter. So as you go across the period, as you go across the row, you have more and more and more protons, and so you're attracting the electrons tighter and tighter and tighter, and so the atom gets smaller and smaller and smaller. So that's the general trend. So I now have a practice problem for you. And this practice problem is just asking you to consider those first two factors. We're going to look at the N value of the valence level and the number of protons in the nucleus. And remember, the first one always wins. If you figure out a winner based on that first rule, based on the N value of the valence level, you do not need to look at rule 2. You've already found your winner, okay? So I've given you various pairs of neutral atoms, and I want you to consider the two atoms in that pair and decide which is the larger atom, and then circle whichever one of those you think is larger, and then move on to the next pair and do the same, and so forth and so forth. So pause the video, go ahead and finish this for each of these pairs, choose the larger of the two, and when you're done, resume the video and I'll work through the answers. All right, resuming the video now, we're going to take a look at each of these pairs and decide which of these is larger. And remember, rule number 1 always wins, and that's the n value of the valence level of electrons. So the larger the n value of their valence level, then the larger the atom. So we're going to look at first at sodium or potassium. And you can see right here that potassium's valence level, it has electrons in the n equals 4, compared to sodium, which has electrons in the valence level of n equals 3. So potassium has a much larger valence shell than sodium does. And so potassium is going to be the larger atom. The next is potassium or calcium. Potassium or calcium. So rule number 1, we look at the n value for their valence level, and they're both in n equals 4. So rule number 1 doesn't help us. They're both tied according to rule 1. We go on to rule 2 and look at the number of protons in their nucleus. Calcium has 1 extra proton compared to potassium. So if calcium has an extra proton, then calcium's electrons are being held tighter to its nucleus, and calcium is smaller than potassium. So potassium is larger. Moving on, potassium or magnesium. Potassium or magnesium. So you notice here, they're not only in different groups, but they're in different rows. But remember, rule number 1 always wins. So if we decide we have a winner based on rule 1, that's the one we go with. Rule 1 says look at the n value of their valence level. For potassium it's 4, magnesium it's 3. Potassium wins. Higher n value for its valence level means it has a larger outer shell of electrons, so it's a larger atom. Next one, lithium or neon. So you've got lithium here and neon all the way across in the same row over here. Well, if they're in the same row, they have the same n value, n equals 2 for their valence level. So they're tied according to rule number 1. But I think you can see that if we go all the way across this row, we continue to add more and more and more protons. So neon has many more protons than lithium does. So neon is attracting its electron clouds much tighter. So neon is smaller than lithium, and therefore lithium is a larger atom. And finally, we look at hydrogen or helium. So hydrogen and helium are in the same row, so they have the same valence level. So according to rule number 1, they are tied. For rule number 2, helium has 1 extra proton, so it is attracting its electrons tighter, and therefore helium is smaller than hydrogen. And so hydrogen is the larger of the two. And this leads us to a general trend that we can draw. This is, if you'll bear with my rough sketch, the periodic table doesn't look exactly like that, but let's imagine that's the periodic table. And we are going to increase size as we go down a group and as we go left across a period. So remember, we get smaller and smaller and smaller as we go right. So we increase as we go left and down. So that might suggest that helium, which is way up here, is pretty small, and indeed it is the smallest of the elements. And that cesium is way down here. It must be pretty large, and it is indeed the largest of the stable elements. So a neat way that this is often represented is with the snowman analogy. So the snowman gets larger and larger and larger as we go down a group, because you're adding larger and larger and larger orbitals in the larger n values for the valence shells. And then to represent this trend within a period, within a row, we imagine that the snowman has fallen over. okay? It gets smaller and smaller and smaller as we go to the right because of additional protons being added to the nucleus, which draws the electrons tighter and tighter and tighter. So we get larger as we go left and down, and that's exactly what this is showing. So this is rule number 1 that talks about the valence levels, and this is rule number 2 that talks about the number of protons in the nucleus. So that's just a neat little graphical way to represent the trend that may make it easier for you to remember. And many of you probably remember these snowman images from your previous chemistry course.